sections on sequences, series, and mathematical induction. So we're going to look at these sections today, 9.1 through 9.4, again on sequences, series. Particular types of sequences and series are arithmetic, geometric. We're going to look at sums as well, and then concluding with mathematical induction. Okay, so what is a sequence? A sequence is a set of numbers written in a specific order that follows a certain rule. So it is, you can also look at it as a function, right? The domain is the set of integers. So right here, we sometimes start with 0, 0, 1, 2, 3, and so on, or sometimes we start at 1. So these are the inputs, right, of our domain. And the values of the function are these terms of our sequence. We label them A1, A2, and so on, right? The terms. So you can think of these A sub n's as the equivalent of a function like f of n. N is the input value. The notation A sub n would be used to denote the output of the n. Okay, so for example, I listed a sequence here. The first term is the 1 right here, and we call that A sub 1. So the input is the 1 for being the first term, and the output is the term of the sequence, which is also 1 in this case. What's the second term? The second term is a 3, so that's A sub 2. So when you input a 2, the output is 3. And continuing on, the third term is a 9, so that's A sub 3. So we plug in a 3, we get an output of 9. So that's an example of a sequence, looking at some of the terminology relating the inputs and the outputs, which are the terms of the sequence. So here's another example. If we want to list the terms of a sequence, sometimes we have an equation that tells us how to get the terms of a sequence. So this is our equation. A sub n equals 3n minus 2. So A sub n is any term in the sequence. When you plug in a value for n, that's going to be the position of the term in the sequence, right? So if we want the first 4 terms, this is going to be similar to evaluating, where we plug in, again, the values 1 through 4, because we want the first 4 terms into our equation. So A sub 1 is our first term. That means I plug in a 1 for n. So this gives us 3 minus 2, which is 1. Then I go to the next term, which is A sub 2. So I'm plugging in a 2 to my equation here. 3 times 2 is 6, minus 2 is 4. I plug in the 3 for the third term. So we see we have a 3 times 3 now, minus 2. So 9 minus 2 is 7. And then I plug in the fourth term. So I plug in a 4 for the fourth term. So 3 times 4 is 12, minus 2 is 10. So they wanted only the first 4 terms. I could get any term of the sequence that I wanted by plugging in the position that I wanted, right? So I wanted the 10th term, I would plug in a 10. But here we just wanted terms 1 through 4. I plugged those in, got the outputs, and that gives us our sequence, the 1, 4, 7, and 10, okay? So next, here's another example. This is an example of a sequence. It's going to alternate signs. And that happens when you see something like this -1 to a power. Because taking a negative number to different powers, odd or even, is going to give you a different sign. So that's how we get alternating signs. But let's look at how we're going to do this one. Again, here's our equation. We want the first 4 terms. So again, we're going to do like we did before. We're going to plug in numbers 1 through 4 for n and evaluate. So the first one is the first term. N is 1. So you see we plugged in a 1 for n. So -1 to the first over 2 times 1. Plus 1, -1 to the first is -1, all over 2 plus 1, -1 over 3. And then we continue this for 2 through 4, right? We plug in a 2, evaluate, -1 squared now is a positive 1. On the bottom, we get 4 plus 1, which is 5. So you already see the alternating signs. And we have a negative raised to an odd power. It stays negative. But here we have the negative raised to an even power. So it's a positive number, right? So we continue on. We take -1 to the third power, plug in a 3 for n down here. We get -1/7. We wanted the first 4 terms. We go up to 4, plug in a 4. -1 to the 4th power is a positive, all over 8 plus 1 on the bottom, 1/9. So these are the terms of this sequence, at least the first 4, -1/3, 1/5, -1/7, 1/9. And again, it would keep going if we wanted to plug in more numbers. And you also see, again, the alternating signs that we have from negative to positive, again, coming from this -1 to the n power, and it's going to change the signs based on the power of that -1. Okay, so here's another one. Write the first 5 terms of the sequence. So we're going to take n from 1 through 5. Okay, here's our equation again. Again, when a is 1, that's for the first term. We have -2 to the first power, which is -2 times 7, which is -14. What about the next one? Next term, we plug in a 2 for n, so our second term is 7 times -2 to the second power. -2 squared, or any negative number to an even power, becomes positive, so that's becomes positive 4. 7 times 4 is 28. Continuing on with a 3, but now -2 to the third power is a -8. -8 times 7 is -56. And we continue on, a negative to an even power, -2 to the fourth power becomes a positive number, positive 16 times 7. And then it goes up to 5 terms. So the previous examples, we only did this 4 times because we wanted 4 terms. This one wants you to take this to the 5th term, so we go up to 5. -2 to the 5th is a negative number. -32 times 7 is -224. So again, these outputs that we got from plugging in the values 1 through 5 are the terms of the sequence: -14, 28, -56, 112, and -224. So we can see here a pattern, alternating signs. Our first term here was negative, and then it was a -2, so every time it was multiplied by the -2. So if you have a sequence that starts with a -1 to the n, like in the previous one, okay, it'll result in alternating signs with the first term being negative, okay? But let's look at this one. We have another one. Now we have another -1, but it's to a power of n plus 1. So we're doing the same thing. We want the first 5 terms. So again, we first plug in a 1 for n. We evaluate here. We get a positive 1. 2 times 1 is 2. We do the same for 2. We're plugging in a 2 for n. Gives us -1 to the power of 3, which is a -1 times 2, which is a -2. As we continue on, we plug in a 3, but now this becomes to the power of 4, which is an even number, which makes that a positive 1. And now we plug in a 4, but we add 1, which is a 5, an odd number, so that gives us a -1 times 2. And one more, because we want a 5. 5 plus 1 gives us a power of 6, which is an even number, which makes it a positive 1. So what do we get here? We get alternating signs, and it's the value 2 just changing from positive to negative, positive 2, -2, and so forth. So these are the first 5 terms. So what can we observe by this one? We also had alternating signs, but the first term was a positive, okay? And then every term after was multiplied by a -1. So this sequence starts with -1 to a power of n plus 1. The other ones are just to a power of n. So whatever n was, either even or odd, that determined the sign. This time it's n plus 1, so whatever you plug in, you add 1 to it, so it changes. And you're going to have alternating signs. This time the first sign is a positive number, okay? So that's just examples of different patterns here. We have different sequences that are going to alternate signs, and that's how we get that one. Okay, so on this new example, we have to write an expression for the apparent nth term of the sequence. So now we're working backwards from the previous examples. Now we actually have a sequence, and we have to find the equation, or here the expression, for these sequences, okay? So let's look at the first one. 1, 3, 5, 7, and so forth. It helps to look at the difference between the numbers here, okay? So the difference between 1 and 3 here, if we do 3 minus 1, we get 2. If we do 5 minus 3, we get 2. If we do 7 minus 5, we get 2. So looking at that, we can say, okay, well, we're going by 2 each time. Let's try 2 times n. Does this fit our expression, or our sequence? So let's check it. If I plug in a value here, let's say I plug in a1, the first term is 1, I should get a 1. So when I plug in a 1 here, 2 times 1 is not 1, I get 2. So remember, when you plug in the position for the sequence, right, you plug in a 1 for first term, the output should be the first term. If you plug in a 2, then you should get the second term, but that didn't work here, so that's not the equation. So let's try similar to it. Let's try 2n minus 1 maybe to give us this sequence here. So let's test it. If we plug in a 1, we should get the first term, which is a 1. So 2 times 1 is 2 minus 1. So we do get a 1, so that works, right? And we can check it for another number. So when I plug in a 4, remember that should give us the fourth term. So 1, 2, 3, 4, that's the 7. Let's check if our equation works for that. 2 times n, 2 times 4 is 8. 8 minus 1 is 7. So this equation does work. So that was a good way to see what the difference was. We worked with the 2. It didn't give us, it wasn't 2n. 2n minus 1 though worked. So we have the equation for this sequence right here, 2n minus 1. Okay, now let's look at the next one. Let's start by doing the same thing, okay? Well, actually, we notice first that we have alternating signs. So we have a positive and negative, positive and negative. So remember, we're going to look at what we observed previously. Okay, assuming n begins with 1, if we have a negative 1 to the power of n, we're going to use that if our first term is a negative number. If our first term is positive, like we have here, though, we're going to take negative 1 to the n plus 1. So this has to be part of our equation because we have alternating signs. So we're going to use one of these when we have alternating signs, whatever works for our sequence, depending on whether or not the first term is positive or negative. Okay, so again, we're going to use that right here, negative 1 to the n plus 1, because our first term is positive. But let's go back, like I was mentioning, let's go back and look at the pattern between the numbers to see if we can find a common difference. If we do the difference between these right here, negative 5 and 2, we get a 3. The difference between the 10 and negative 5 is 5. And the difference between negative 17 and 10 is 7. So I don't have a constant difference like I did before. But what I can do is take the differences of these again. The difference between 5 and 3 is 2. Between 7 and 5 is 2. So now I have a constant difference. So how does that help? Well, however many times it takes us to get to a common difference can help determine the type of equation it is. It took us 2 times of taking differences of our sequence, right? We took the differences here. We got these numbers. We took the differences again, and we had the same difference. So because it took 2 times to get a common difference, that means power of 2, it should be a quadratic, right? Because it took 2 stages to get the same difference. So let's play with that. Let's try something just n squared, right? Again, let's try it. So if we plug in a 1, first term is 2, output should be 2. So when I plug in a 1, 1 squared is 1, not 2. So this one's not working, okay? There's going to be something with a squared. So let's just try an n squared plus 1 this time, okay? Last time I got a 1. I need a 2, so plus 1 makes sense. And again, we're starting with quadratic. We know we're quadratic because it took us 2 levels to get a common difference. So let's try this one, plug in a number. First term is 2, so when I plug in a 1, I should get a 2. So if I plug in a 1, I get 1 squared plus 1. 1 squared is 1 plus 1 is 2. That works. Let me just double check it. Again, I'm going to plug in a 4. I should get the fourth term. 4 for n, 4 squared is 16. 16 plus 1 is 17. It should be a negative 17, but that's going to come by adding this right here to our equation once we find it. So it does work. It gave us the 17, so we know that it's n squared plus 1. But then, again, because signs are alternating, we add this. We add the negative 1 to the n plus 1, again, as we determined before. It's going to compensate for the alternating signs. And again, we use that version of it because the first term is positive, okay? So some ideas here for how you guys can write the equations when you have the sequence, okay? So continuing on with sequences, we have a sequence that is called a recursive sequence. So what does that mean? Sequences are defined recursively when you have to use the previous terms to determine the next terms of the sequence, okay? Here's an example of recursive sequence. We have to write the first 5 terms. Oh, sorry, I thought I was going to sneeze. We had to write the first 5 terms, but we have to use the previous terms. So right here we have a sub 1. The first term is 3. The next one, they use k. A sub k is going to be 2 times a sub k minus 1. So that's the previous term. So whatever ak is, when you're minusing 1, you're getting the previous term. So in this case, we plug in the previous term 3 plus 1. K has to be greater than or equal to 2 because we at least have to start with the second term given the first term. Okay, so how are we going to write this one? We're going to work it the same. We still plug in the values, in this case for k instead of n, right? First term is given, a sub 1 is given, and we need that. So how are we going to find the next term? So a sub 2, we plug in a 2 wherever we see k this time. So it's going to be 2 times a sub k minus 1, 2 minus 1, plus the 1. Right here, 2 minus 1. So the subscript for a, 2 minus 1 is 1. So what does that mean? That means we take 2 times the a sub 1, which is the previous term, plus 1. The previous term is 3. 2 times 3 is 6, plus 1 is 7. So now we have that term. So continuing on, when I plug in a 3, right here, I get 3 minus 1, which is a sub 2. So that's the previous term. So now right here, I need to plug in the previous term, which is 7. For this equation. So 2 times 7 is 14, plus 1 is 15. And that continues on. We plug in a 4 for the fourth term, so I need a sub 3, the previous term that I got, which is 15. So 2 times 15 plus 1, which is 30, plus 1, which is 31. So we're going up to 5, so I plug in a 5. I want 2 times a 4, which is 2 times the previous term. 2 times 31 is 62, plus 1 is 63. So that's how we use a recursive formula. We're always using a previous term of the sequence to get the terms of our sequence. Okay, so here we list the 5 terms of the sequence that we got. The first one was 3, and then we found 7, 15, 31, and 63. Here is another example of a recursive sequence. In this one, they're giving us the 2 previous terms. So we haven't seen one like this where it starts at a sub 0. Okay, so that's a sub 0 instead of a 1 for the first term, so keep that in mind. A sub 1, and then all other terms are defined by a sub k, which is a sub k minus 2, which is 2 terms before this one, right? So if I want, for example, I'm going to plug in the 3's to start. I'm going to want 2 terms before, or I'm sorry, we're going to plug in a 2 to start, so I'm going to want 2 terms before that, which is going to be the a sub 0 term, plus 1/2 times a sub k minus 1, that's going to be the previous term. So what does that look like as we're plugging the values in? Okay, we have a sub 0, a sub 1. So our next one we're going to plug in is a 2 for k, right? Here's our equation again, so we plug it in. So for k, I plug in a 2 right here and right here. So I get a sub 2 minus 2, which is a sub 0, which is 2 terms previous, plus 1/2 times a sub 2 minus 1. 2 minus 1 will be the previous term, a sub 1. So again, that's what I was mentioning, a sub 0 plus 1/2 a sub 1. A sub 0 is 1 plus 1/2 times the previous term, 2. 1 plus 1/2 times 2 is 1. I get a 2 for that one. Okay. Continuing on in the same way, I'm plugging in a 3 now. 3 minus 2 is 1, so I want a sub 1, which is 2 terms before, plus 1/2 a sub 2, which is the previous term. So plugging in the values, a sub 1 is 2, a sub 2 is also 2 here. So 2 plus half of 2, 2 plus 1 is 3. And again, we plug in the 4, we get a sub 2 plus 1/2 a sub 3. So plugging in the values, a sub 2 going up 2 terms before is a 2. And then the previous term is 3, 1/2 times 3 plus 3/2, and we get 7/2. So remember, we started with a sub 0, so our actual 5th term is coming from a sub 4. So we have 1, 2, 2, 3, and 7/2 as our first 5 terms for this one. Okay, the first 2 terms on this one were given. Okay, so you're also going to see some factorials. So let's look at what that is. If n is a positive integer, n factorial is defined like this. It looks like n, or any number, with an exclamation point. So what does that mean? That means whatever n is, you multiply all numbers from 1 up until that number consecutively. So let's say n is 7, and you have 7 with an exclamation mark next to it, 7 factorial. That means you're going to multiply numbers starting at 1 times 2 times 3 times 4 all the way up to 7, okay? So whatever n is right here, you take n, so it's going to take 1 times 2 times 3 times 4 times all the way up to what that number n is. N minus 1 would be that number previous, right? So in the example I said, if we're doing n factorial and say n is 7, I multiply all numbers times each other, all our natural numbers times each other up to 7. So it's 1 times 2 times 3 times 4 times 5, all the way up to times 7. The previous number would be times 6, and then times 7. Okay, so here's another way to look at it working backwards. You can take that number n, whatever that is, and you can start there. So again, in my example, let's say n is 7. We're going to multiply all numbers from 7 on down to 1. So it'd be 7 7 minus 1 times 6 times 5 times 4 times 3 times 2 times 1. We can just look at it in the other way as well. Keep in mind a special case for our factorials. 0 factorial gives you a 1, not 0. Keep that in mind if you ever need to evaluate 0 factorial. For some numbers, you should also have be able to evaluate in your calculator. You should have this exclamation point button on most calculators. So if you needed help, reach out to tutoring to look at your calculator as well and look at how to evaluate some of these that you can evaluate with a calculator. Okay. So how are we going to evaluate or find the terms of a sequence such as this one that involves a factorial down here, okay? So they want us to find the first 5 terms of this sequence. We have to start with n equals 0 this time. So here it is. We just do like we've been doing, plug everything in. N is 0 though first because it tells us to start at 0. So a sub 0 equals 2 to the 0 over 0 factorial. Anything to the 0 power is 1, and I just mentioned 0 factorial is also 1, so this gives us 1 over 1, or 1. Again, don't forget 0 factorial is 1. It's good to know these. We can evaluate these by hand, but again, you can always double check with your calculators as well once you find the factorial button. The next term will be a sub 1, so we plug in a 1. 2 to the first is 2 over 1 factorial, which is just 1. 2 over 1 is 2. Plugging into 2, we have 2 squared over 2 factorial. 2 squared is 4. 2 factorial is 1 times 2. 4 over 2 is 2. 2 to the third is 8. 3 factorial is 1 times 2 times 3. All numbers being multiplied up to 3. We get 8 over 6. Don't forget, you always reduce. That reduces to 4 over 3 when you divide both of these by a 2. A to the sub 4, so it's 2 to the 4th power. I'm plugging into 4. 2 to the 4th is 16. 4 factorial is 1 times 2 times 3 times 4, which is 24. So that's how we got the denominator. So we get 16 over 24. Again, always reduce. That is 2/3. So this one at the first 5 terms, we stop when we plug in a 4 because we had a sub 0. We started with 0. So at 4, we already have our 5 terms. So here are the terms of our sequence. The outputs we got 1, 2, 2, 4/3, and 2/3. Okay. So again, if you have numbers and you need to simplify the factorials, I would suggest use your calculator. But what if we have something like this, an n plus 1 factorial over an n? So let's look at what this means and how we would simplify it. Well, looking at the definition, we know that n factorial, let's start with there. N factorial is multiplying numbers from 1 all the way up to that number n, right, in consecutive order. So 1, 2, 3, 4, all the way to what n is. So that's another way to expand and write n factorial so we can see what's going on here. Well, on top in the numerator, I have n plus 1 factorial. So what does that mean? So that means I'm going to go all the way up to n, multiply all that, and then times one more number times n plus 1. So in the example I did before, if n was 7, 7 factorial, and the bottom would just be all numbers multiplied from 1 to 7. So what would n plus 1 be? That would be 8 factorial. So it would be 1 times everything time up to 7 times that extra 1, 8. So just to kind of give you an example. So I wanted to write it out so you can see what that means, right? But again, so this n plus 1, this includes just n factorial. So this part right here is n factorial times an n plus 1. On the bottom, again, it was just n factorial, which I expanded. So we can write it like this, right? So again, this first part is that n factorial. This bottom part is also n factorial. So what do you notice? They cancel, or the same. And what's left is this n plus 1. So that's one way to simplify these. Maybe just expand them, write it out. To kind of see what they are, and then cancel anything that's the same. So again, on top we have an n factorial times an extra n plus 1, but on bottom was n factorial. It all cancels out, and so this simplifies to just n plus 1. Okay, it'd be similar with an n minus 1. You would just go 1 less than where n was. Okay. Okay, so let's talk about summation now. Okay, so this is your symbol right here. It's called a sigma. This is your symbol, which is your summation, which means to add up everything that we produce from here, right? So the sum of the first n terms of a sequence, we could represent it by this. I is our index of summation down here. N is our upper limit. And the 1 in this example is our lower limit. And right here, the a sub I, this is usually a formula or something that we're going to plug these values in to generate the terms here. And because it's using this sigma notation or a summation notation, that means everything we output we're going to add. Okay, Index, we start at 1, so that's the first number you plug in. So we plug in a 1 to whatever formula they give us here to give us our a sub 1. And then we're going to plug in a 2, a 3. We keep going all the way up until this number n. So if n was a 4, we're going to plug in a 1, then we're going to add, then plug in a 2, then we add with what we get when we plug in a 3, all the way up to 4. Okay, so it'll help by looking at an example. We have these 2 examples that we are going to look at. So let's continue with those. So the first one, right? Again, this is the notation for sum. So it's telling me I'm going to find the sum of all the numbers I generate right here using this formula 3i, of the numbers that I get from plugging in a 1 all the way up until a 5 consecutively. So what does that look like? So 3i, when I plug in a 1, is 3 times 1. Then sum, I'm going to add, plug in a 2, 3 times 2. Then I plug in a 3 for I, then a 4, and then I stop when I get a 5. So this is what I generate by plugging in the numbers from 1 through 5 into my equation. I'm going to add them all up, but first I'm going to simplify each term. Okay, so what I get, 3 times 1 is 3, 3 times 2 is 6, plus 9, plus 12, plus 15. Add all of that up and we get 45. So that's what we did here. We found the sum, and that's how we interpret also this, the symbols and what it all means. Okay. We have one more example right here. So let's look at this one. It's our summation notation. Here's our equation. It's in terms of k. So k, we're going to start with k equals 3, and we're going to plug numbers in all the way up until we get to 6, and then we're going to add all of those up. So what does that look like? So it's going to be 1 plus k, which is going to be 3 first, 1 plus 3 squared, okay? And then I continue on. I plug in a 4 for k, 1 plus 4 squared. Then I plug in a 5 for k all the way up to 6 because my upper limit was 6. So this one went from 3 to 6, plugged in all those numbers, and then I have to add them all up, hence the sigma notation or the sum. Okay, so 1 plus 3 times 3 squared is 9, 1 plus 9. This is 1 plus 16, 1 plus 25, 1 plus 36. Gives me what? 10, 17, 26, 37. Add all of that up, I get 90. So the sum for this is 90, and I think that's pretty cool. The symbol right here tells us to do all that, and this has an output of 90. Okay, so some more. Consider an infinite sequence. That means it goes on forever, right? The sum of the first n terms of the sequence is called a finite. So if we have a set number of terms we're going to add up, it's a finite one. That's also the same as an nth partial sum. So we're going to add up only to an n value. And it got cut off right there, but that's an n. So we add up the values. If I starts at 1, we plug in numbers all the way up to n, and we get those values right there, right? The sum of the terms of an infinite sequence, so that means the sequence keeps going on forever. We can look at it like this. We have from I all the way to infinity. And that's how we would mark that one, and that's what it looks like. It doesn't stop, it just goes on forever. So we looked at one like part 1 before. We did those in the previous examples, but the new one right here is looking at an infinite series or an infinite sum, and there is a formula for those that we're going to get to right now. Okay, so here we have this one. We have our sigma notation. Here is our formula, 3 over 10 to the power of I. I starts at 1 and we go up to infinity. However, it says A, find the third partial sum. That means don't find the sum all the way to infinity, just find the sum up until the third term. Okay, so that's going to look similar to what we just did, third partial sum. So I'm not going to go to infinity, I'm going to go up to 3, and I'm going to plug in numbers from 1 to 3. So I have 3 over 10i. I is going to be a 1, a 2, and a 3. When I evaluate these, I'm using, write them as decimals. I get 3 tenths, 3 hundredths, and 3 thousandths. When I add 0.3 plus 0.03 plus 0.003, I get 0.333, and it stops there. So that would be my third partial sum. So yes, it was up to infinity when it was presented, but to find the third partial sum is to only find it with 3 terms. If it was fourth sum, I would only find it up until the first 4 terms and so on, right? But let's look at B. It says to find the sum as it is, that's presented, and that means it goes to infinity, okay? So this is what we get. we can observe a pattern here as well. So 1 to infinity, I'm not going to be able to plug in all of my numbers all the way to infinity, but just to kind of see a pattern, what are we getting? I plugged in the first few numbers, right? So I is 1, then I is 2, 3, 4, 5, and so on. Again, yes, I do want the sum to infinity, but I just plug in a few numbers to get a pattern here. Writing these as decimals, I get 0.3, 0.03, 0.003, 0.0003, right? And so on and so forth. If I add all of that up, you can see that it's going to be 0.33333, continuing on forever. That's the value that we get. So on some of these, you're going to be able to write them as fractions as well. If you need to go over that, you can reach out to your instructor to tutoring. If you have a decimal that goes on forever, but it has a pattern, you can always write those as a fraction. And there's a formula to go over if you need to go over that. Some of them you might just know or have memorized. So hopefully you can see that 0.333 repeating forever is actually the equivalent of the fraction 1/3. So it's pretty cool. This should go on forever, but because the number is less than 1, because it's a decimal value, you think, oh, it's going to go to infinity. But it's a decimal value, so the values are getting smaller each time. So we actually can get an actual value, which would be 1/3, okay, for this one. So that works if you have an infinite sum. As long as the values are less than 1, we can get an actual sum value, okay? Okay, so now we're going to move on to another section maybe you've seen on a specific type of sequences, and that's going to be our arithmetic sequences. Okay, so what is an arithmetic sequence? An arithmetic sequence is a sequence where the difference between our terms is always the same. So we have an example here, a sub 1, a sub 2, a sub 3, and so on, right? If it's arithmetic, then we can subtract the next term minus the term before it. So in this case, a2 minus a1. You can also subtract a3 minus a2, a4 minus a3, and so on. It will be the same number. You're going to have a common difference amongst them. So that's what makes a sequence arithmetic. Okay, so some examples, instead of just using our a values, let's look at another one. We have this sequence here, 7, 11, 15, 9. If we subtract a term minus the previous term, we should get the same number every time. So right here we did 11 minus 7, which is 4. If we do 15 minus 11, we should also get 4, and we do. 19 minus 15, get 4, and so that's the pattern there. That works. What about this one? 2, -3, -8, -13, and so on. Let's just subtract. -3 minus the previous term. -3 minus 2 is a -5. -8 minus a -3, so we'd have to change the sign, so it becomes -8 plus 3. We also get the -5, and so on and so on. So that's our common difference. So these again are examples of an arithmetic sequence. There's a common difference between all the terms. So an arithmetic sequence has a formula that we can use. If we know it's arithmetic, we can take any term, a sub n, and find it this way by plugging in what the first term is, a sub 1. You plug in the n that you want to find, minus 1 times that d, that common difference, okay? So that's a formula we can use when we know a sequence is arithmetic. So, for example, here, find a formula for the nth term of an arithmetic sequence, which is right here. They have a formula set up for us, a template for a formula we can use, right? The common difference is 3, so I know I'm going to plug in 3 for D, and I have the first term. The first term is 2. So again, we have a common difference 3. We have a first term, a sub 1 is 2. If I just plug these into my formula, here's my formula, then I have a general formula, right? So any a sub n is going to be a sub 1, which is 2, plus n minus 1 times that common difference is 3. So if you want a general formula for any arithmetic sequence, we plug in the values a sub 1 and the d. We're going to simplify here. We're going to distribute the 3 into the n minus 1. So we get 3n minus 3. Combine like terms, 2 minus 3 is -1, so we have 3n minus 1. So that's our formula, given that we know we have an arithmetic sequence, and we know our d, and we know our first term 2. Plug everything in, and we simplify, and that is our formula for an nth term. Okay, let's do another one. We know that the fourth term of an arithmetic sequence is 20. The 13th term is 65, but this one's not asking for a formula. It's asking to write the first 11 terms of the sequence. Well, let's first see what we have. And well, I guess what we need to find the first term and the difference to help us, right? Now, here's where we write what we have. The fourth term, our a sub 4 is 20. The 13th term, or a sub 13, is 65. So if I write out slots for all the terms in my sequence, well, at least up to 13, right? Let me plug in the ones that I know. So the fourth term right here, if you count 4 spaces, that's 20. The 13th term over here is 65. So we know it's arithmetic. There should be a common difference. So it would be the same number that we add right here each time to get up to the 65. So what we can do is we can look at, okay, well, how far apart are we from the fourth term to the 13th term? And then what's the difference between the terms here? So there's 9 terms between these two, between 4 and 13, and the difference between these two is 45. If we take that difference divided by the difference in the terms between them, we get the common difference, okay? So to simplify, what you can do in an instance like this, arithmetic sequence, and you have certain numbers in the sequence that are spread out, right? Take those two numbers, so a 13th, the further one, equals 65. A4 is 20, and what we're going to do is we're going to subtract them. You subtract their position here, 13 minus 4, and then you subtract their value, 65 minus 20. So 13 minus 4 is 9, 65 minus 20 is 45, and that's what you divide, 45 by 9. And that's how it works, again, to find the common difference. Because we know that it's the same number each time. So we know it's 5, right, or whatever number it would be. We know we're going to plus 5, plus 5, plus 5, plus 5. And we know we do that 9 times, well, we can take the value that we got from going from one point to the other, which was 45. If we divide that by 9, right, that's going to give us the value. That's going to give us the value we added each time. So actually, I'm going to show you how to do this with the formula. But now that we know the difference is 5, you can get the terms that you need. We can, from here, just add 5, right? 25, 30, 35, and so on. To go backwards, we would minus 5. So minus 5 from 20 would be 15, 10, and so forth, right? So you can do it like that. But if you wanted to use the formula, or your professor wants to show you the formula, or just to get practice using the formula, we can do that as well. So now that we know our common difference, right? We know another term. We know a sub 4 is 20. Let me plug in what I have. So I have a specific term, so a sub 4. I don't know a sub 1. I'm going to solve for it. But I have the n, I'm using 4, and I have my difference, which is 5. A sub 4, I have to actually plug in the value, which is the 20. I have everything else that I need. I'm going to solve for the first term. 4 minus 1 is 3. 3 times 5 is 15, minus 15 on both sides. So a sub 1 is 5. So now that I have a sub 1 that's 5, again, I have D. I can just keep adding 5 each time, right? I can generate as well from the formula. So down here, I have the formula. I can simplify it. So a sub 1 is 5, plug that in. D is 5, and just like we did previously, simplify. So 5 times n, 5 times negative 1, 5n minus 5. The 5's cancel, 5n. So I could use the formula as well. I wanted to show you that. And I could generate any term that I wanted. If I wanted the next term, a sub 2, plug in a 2 for n. 5 times 2 is 10. So we could do that, but again, you just need the 11 terms. So just knowing the difference is 5, we're going to add 5 each time, right? So 5, 10, 15, 20, 25, 30, so on and so forth, 35, 40, 45, 50, 55. Now remember, 65 was the 13th term. I used it to help me find the values, but I only needed the first 11. So I can go ahead and stop right there. And these are the first 11 terms of my sequence. Okay, so again, I went over how to use the formula to help you find the first term, solving for A1. We can then get a general formula and use that to get the rest of our terms by plugging in the term number, 2, 3, and so forth. But again, once you have your D and you know it's arithmetic, you can just keep adding or subtracting that D to go backwards and get your values. Okay, so we have a recursion formula, but we want to find the ninth term of the arithmetic sequence. We have the first two terms, which are 2 and 9. How do we find the ninth term? Well, we have the two terms. It's 9 is arithmetic, so it's going to have a common difference. So we start there. The difference between 9 and 2 is 7. So I can start there. If A1 is 2, D is 7, I could really just keep adding 7 now each time to all my terms until I get to the ninth one, which I have seen students do, which is fine and it works. But what if they want you to find the 109th term? Instead of adding 7 each time until you get to the 109th term, we can just plug this in and get a general formula to find the term that we need. So I have my D value. I have my A sub 1 value, which is 2. Plug everything in to get a general formula for an nth term. So it stays in terms of n. So 7 times n, 7 times -1. 2 minus 7 is -5. 7n minus 5. Here is my formula. So now if I want the ninth term, I can just plug in a 9 because I want a sub 9. So n is 9. Plug in a 9 right here. 7 times 9. 63 minus 5, my ninth term is 58. So again, finding the ninth term, we have the first and second. We know the difference is 7. We can keep adding 7 each time till we get to 9. Or we can use the formula. And again, the formula would come in handy, especially if you want to find terms that are larger, right? Or larger in the sequence, okay? So we can also find sums of arithmetic sequences, finite arithmetic sequences. We have a formula here, right? S sub n equals n over 2 times a sub 1 plus a sub n. Based on the fact that we have the pattern, and I kind of like to explain this formula. There was a mathematician that his teacher told him to add up all the numbers from 1 to 100 or something, and he found that well, not to get into too much, but he just discovered that formula. If you take the first term and the last term, which is what this is, you take the first term, you take the last term, you add them up, and then you just multiply times the number of terms you had, right, over 2, which is half, because they're all going to work out that way with the formula. Anyway, that's just a cool little backstory if you guys want to look it up about the story about the mathematician who came up with that formula. Instead of adding up all the numbers, for example, from 1 to 100, he found the pattern and did that quickly. So that's what we're doing here, right? Because you're presented with something like this, find the sum. Okay, so you think, oh, okay, I need to add 1 plus 3 plus 5 plus 7. But if we know this is arithmetic, no, we can just plug it into the formula. And that requires, again, just knowing the first term, the last term, and just count the number of terms, which is our n. And we have it all here, right? So our first term is 1. 19 is the 10th term. If we count, there's 10 terms. The 10th term is 19. So how many terms again? 10. So this is all the information that I need to plug in, and I get the sum instead of adding every single number up, right? So the sum of these 10 terms, n is 10, 10 over 2, times 1, my first term, plus 19. 1 plus 19 is 20. 10 over 2 is 5. 5 times 20 is 100. So there's a lot of formulas that we're using in these sections here. So ask your instructor. I don't know how it works, if they are going to let you have a formula sheet or you need to memorize some of the formulas. But a lot of these problems that we're going over have formulas that can be used. And if you know how to properly use the formula for the right problems, it's not too bad knowing what you have to do, right? So this is an example. If we know the formula we have to use and we know that we can get these values and plug them in, that's not too bad, right? So concentrate on that. Have your toolkit, have your formula sheets nearby, and just practice knowing which formulas to use for what problems, right? So how do we find a partial sum of an arithmetic sequence, okay? We have this sequence here. We need to find the 150th partial sum. So we want the sum for the the first 150th terms, right? So again, like the previous one, if I were to list out all the 150th terms and then add them, that would take too much. But if we know there's arithmetic, right, has that pattern, we have the formula. So for the formula, we need to add, we take the first term, we need the last term, and then we need the number of terms. So I have the first term, I have the number of terms, 150, but I need to find the 150th term. So if I'm going to plug this into a formula, I also need the difference, the common difference. So that's why I'm subtracting here. 16 minus 5, I get 11. So I'm going to use that common difference to help me find the 150th term. So first I'm going to just find a formula for the sequence right here. So I have a sub n, a sub 1 is 5, times n minus 1 times d, which is 11. Again, distribute here, so it's 11n minus 11. Simplify, 5 minus 11 is negative 6. So a sub n, so to find any term from this sequence, again, using the general formula to find the terms of an arithmetic sequence, I plugged in the first term in my difference, and here's the formula. So now I'm going to use that to find my 150th term, right? So n is 150, plug that in. Times 11 minus 6 gives me 1644. So now I use my sum formula, right? I needed the first term. I needed the 150th term. I know there's 150 terms. That's my n. So all of that gets plugged into the formula. So the sum for the first 150 terms of this sequence is the 150 over 2 times the sum of the first term plus the very last term. So when I add that up, plug that into my calculator, the sum is 123,675. So it was much easier to use a formula to get that than to start adding and finding all the 150 terms, right? Okay, so you also look at geometric sequences in the next section. So what is that? So a geometric sequence is a sequence where the ratios of consecutive terms are the same, meaning that you're always multiplying by a certain number each time to get the next numbers, right? With arithmetic, you're always adding another number each time. With geometric, you're always multiplying by the same number to get the next numbers. We can find that by looking at the ratio. So with arithmetic, we were subtracting a term minus the previous term. Here we're dividing a term by the previous term, and you should see that same number, that same ratio. So right here, A2 divided by A1 should be the same as A3 divided by the previous number, A2, and so on, okay? So we have some examples to see some numbers here. Look at the first one. If we take 4 divided by 2, we get 2. 8 divided by 4 is 2. 16 divided by 8 is 2. That's the common ratio that we have. That's geometric. Here's another one. 36 divided by 12 is 3. 108 divided by 36 is also 3. We continue on. We know that ratio is 3. So to generate further terms of the sequence, we can keep multiplying by 3 each time. And we have this one. It works with fractions as well. 1/9 divided by negative 1/3 gives us negative 1/3. So negative 1 over 27 divided by 1/9 should also be 1/3, and so on and so forth. And you can see in the formulas that ratio is what's raised to a certain power. So in this one, the ratio is negative 1/3 to the n. That's the formula. This one, it was 3 to the n, so that's part of the formula. And this one, the ratio, common ratio is 2, so you're going to see 2 to the n in the formula as well, so that helps. Okay, so we also have, just like we have for our arithmetic, we have a formula for any term of a geometric sequence. If you know a sequence is geometric, you can obtain any n term of the sequence using this formula. You would need the first term, a sub 1, and you would need that r value as well. But then you can just plug in the n and get any term of the sequence, right? Okay, so for example, here's another way to look at it. You have your first term. To get the next term, you times r. So it's the first term times r. Then you're going to take that term times r, since times r squared. And then you take that term times r, you get r to the third. So you can also look at it that way, and that's where the formula gets generated. It's always a to the first multiplied by r so many times, right? It's 1 minus the term value. So if we want to write a geometric sequence, we know the first term is a to the third, and the common ratio is 2. I'm going to show you using the formula, but really you don't need it if you're just writing to write the 5 terms. You know the first term is a 3. If you know the ratio is 2, that means you're multiplying times 2 each time to get the next term. So 3 times 2 is 6. That's the next term, and then you do that times 2, which is 12, and that one times 2 is 24, so on and so forth. But we're going to look at it using the formula just to get an idea of how the formula works, right? We know a sub 1 is 3. We have the r value, which is 2, and I'm going to plug them into our general formula up here, right? a1 is 3, r is 2, and then you're just going to find all the other terms by plugging in the n values, right? So the next one, we plug in a 2 for n. So it's going to give us 3 times 2 to the 2 minus 1, or to the second power, which is 6. And we can keep going. We can plug in a 3 into the formula, which is 3 times 2 squared. 3 times 4 is 12. Plug in a 4, 2 to the third, which is 8. 3 times 8 is 24. And we can plug in a 5 to the formula. 5 minus 1 is 4. 2 to the fourth is 16, and we get 48. But that was the same thing I told you guys, just knowing that a1 is 3, knowing that the ratio is 2, we're just multiplying by 2 each time. So a1 is 3 times 2 gave us the next term 6, times 2 is 12, times 2, and times 2, and so on. Okay, so knowing just that, we can work with that as well, but knowing how to use the formula, because we will need that for some other examples as well, works. Okay, so how do we find the 15th term of a geometric sequence if the first term is 20 and the common ratio is 1.05? Well, we have what we need to write our formula. We have the first term is 20, we have r is 1.05, we want the 15th term, so let me just get my general formula for any term, plugging in a1 20, plugging in 1.05 for r. We want the 15th term, so n is 15. Ends up that we want to do 20 times 1.05 to the 14th power. Use your calculator, and that should be the 15th term. If we're rounding, that's 39.6 for that one. Okay, so that's how we use the information for a geometric sequence, and we use the formula to do that one, right? Okay, here's another one. We're going to find the formula for the nth term of the geometric sequence, and then also find the 12th term. So first we need to find the formula. It says find the formula. We know a sub 1 is 5. We also need r to use our formula, right? So remember, we can take r by dividing to find the common ratio. So 15 divided by 5 is 3. 45 divided by 15 is 3. So that's giving us r, the ratio, right? Like I just mentioned. So I can plug these in to find this general formula. A1 is 3, A1 is 5, R is 3. So here's my general formula to find any term of a geometric sequence. It specifically wanted what? The 12th term. So when I plug in a 12, a sub 12 is 5 times 3 to the 12 minus 1. 12 minus 1 is 11. 3 to the 11th times 5. That's how we find the 12th term, 885,735, right? So again, we know the ratio is r. We can keep multiplying times 5, times 5, times 5, up until we get to the 12th term, but sometimes that takes too long. Knowing the formula and how to work it is a bit more efficient sometimes. Okay, finding the terms of a geometric sequence. This is similar to what we did for the arithmetic sequence. We know the 4th term is 125. The 10th term is 125 over 64. What is the 14th term? I'm going to look for r and a1. What do I know? I know a sub 4 and a sub 10. I want a sub 14. Well, I am going to go back and use the setup that we did for the geometric. It's going to be a little bit different, but the idea is the same. So I want to know a sub 14, which is the last one. I know a sub 4 is 125. Here's my 10th slot. A sub 10 is 125 over 64. Here's the one I want. Now, if you remember previously, we looked at the difference between the terms, and we looked at the difference in the position of the term as well. We subtracted them, right? That's going to work for arithmetic. When it's geometric, keep that in mind. The idea is similar. Okay, we're going to want to use the general formula. We're going to plug in the values for each one, but then we're going to divide our values. So we have a sub 10, okay? Plugging that into the general formula, I don't know a sub 1, but I can plug in my n is 10 minus 1, and I know a sub 10 is 125 over 64. Plug in a sub 4. I know that n is 4, and I know that equals 125. So instead of subtracting like we did for arithmetic, we're going to divide these. And what happens? The a1s cancel. 10 minus 1 is 9. 4 minus 1 is 3. When we divide a variable to a power by a variable to a power, we subtract the powers. So we get 9 minus 3. When we divide these numbers, 125 over 64 divided by 125, I end up with 1 over 64 equals r to the 6. 9 minus 3 is 6. How do I find the ratio, get r by itself? I either take the 6th root or multiply or take it to the 1/6 power. So again, you would use your calculators. We either take the 6th root of r or take 1 over 64 to the 1/6 power. And that actually gives us 1/2 for r. So we can use that now in a formula, get a general formula to find a sub 1. So we have the formula, we know a sub 4, I'm plugging in those values. A sub 4 is 125, plug in the 4. I'm solving for a sub 1. 1/2 to the 3rd is 1/8. I need to solve for a sub 1, so times 8 on both sides. 125 times 8 is 1,000. I use the r value that I found. I use my a sub 1 value. And I have a general formula now with a sub 1, 1,000, r is 1/2. I can use this to find any term in the sequence, any term n. I want specifically the 14th term, so I plug in 14. Use your calculator and evaluate 1,000 times 1/2 to the 13th power, and that's what we get, okay? So I'm kind of short on time. I'm probably just going to skip and just do one more example for you guys, okay? Just to hit on an example using mathematical induction, and that would be the last thing that you guys are seeing in this sections, right? So again, just to review, take all the formulas we have. Some of the slides I didn't go over, just cover how to find sums and other values, but you have formulas you can plug in. So one more example, let's finish this one up with an induction example. We're going to use mathematical induction to prove this formula here. So we have S sub n, which is a sum. You have a sum of all these numbers, 1 plus 3 plus 5, all the way on. Keep going, and the formula there ends up being 2n minus 1 for each number. It says that it equals n squared. So we're proving that. Does that work, right? We're proving that works for all integers n greater than or equal to 1. Okay, so here are the steps for mathematical induction. You have to first prove that this statement right here, this S sub n statement, is true for any n. Usually we use 1, but really you can plug in any n on both sides and make sure that they equal out and are true. And if so, then you assume that the statement is true, and then you got to assume that it's true for the next term in the sequence. So you have to show that it's true for s sub k plus 1, adding the next term. So let's go through it, right? Here's our statement again, s sub n. Number 1, show that it's true for n equals 1, or really any value for n equals anything, right? We usually choose 1. So what does that mean? That means we have to plug in the 1 on both sides to see that it works, okay? And the reason 1 is the best one is because we're only looking at that first term, right? The 1, and we plug in a 1, right? If we were going to use 2, then we're looking at the 2 terms over here, and you're plugging in a 2 over here, whatever, right? So here we go. This is the formula. The first term is 1. Does that equal n squared when I plug in the 1 on both sides, right? So the left side, 2 times n minus 1. The right side, n squared. If I plug in a 1, does it work on both sides? If I plug in the 1 here, I get 2 times 1 minus 1. 2 minus 1 is 1. If I plug it in over here, I get 1 squared. 1 squared is 1. So it does work for that first term. It does work for 1, so that's check. It's true. Step 2, now we can assume that this statement is true for some number. So we're going to write it in terms of k. So we haven't proved s sub n true. We have proved that it did work for the first term, so that's why we changed the variable. So assume that it's true for some value, that's why we call it k, and so we write everything in terms of k. Okay, that's the second step. That's it. We just write our statement in terms of k, prove that's true. Now, how do we prove this is true for one more term, which would be the k plus 1 term? So we plug in a k plus 1 on both sides. So if this is our formula for k, right, we're going to plug in a k plus 1 here. So 2k plus 1 minus 1. But then it should equal to the other side, it equals to k, but if we're plugging in k plus 1, it should equal to plugging in a k plus 1 on the other side squared. So we're proving this whole thing right here, okay, adding in that next statement. Okay, well, it helps that we assume that this whole statement is true because this is our whole previous statement. 1 plus 3 all the way to 2k minus 1. This is our s sub k. We assume true, so all this equals k squared. So we can replace all of that with k squared. And then we have plus 2k plus 1 minus 1 on this side. If we distribute, it's 2k plus 2 minus 1. So everything on the left side is k squared, again, which we got from here, plus 2k plus 1 minus 1 plus all this. We got to show that this is going to simplify or equal to have on the right side. So you can kind of choose to work on either side. It just has to match up. So I'm just going to keep working on the left side and simplify this to see if I can't get what's on the other side, my right side. Continuing simplifying here, 2 minus 1 is 1. So I have k squared plus 2k plus 1. It looks like this is in factored form, so let me see what I get when I factor this. It factors to k plus 1 times k plus 1, which is k plus 1 squared. So check, I got it. So simplifying on the left side did give me what I have on the right side. Thus, that was the last step to prove that that statement was true. So one quick example there on mathematical induction. Definitely always reach out to your instructors, to tutoring for any other questions that you guys may have. But that'll be it for today if you guys don't have any other questions.
Thank you, Ms. Camarillo. We appreciate you presenting for us today. I would like to take a moment to invite everyone to next week's sessions. Whoops, where'd my share file go? I'll put it back up, just a moment.
Oh,
All
sorry.
right, it's okay, no problem. All right, so today, this afternoon, we're gonna have a presentation at 1 p.m. for credit card debt. It's presented by our very own Enrique Lechuga from the Mission Del Paso Tutoring Center. Also, next week, due to the holidays, we will not be having a session, but the week after that, on April 10th, we'll start up again for Math 1332, Measurement, Basic Concepts of Euclidean Geometry, Perimeter, and Area. For Math 2412, it'll be Binomial Theorem and Counting Principles. And for the 1 p.m. session, we'll be having Microsoft 365 and OneDrive with Miss Janine Rudnick. Thank you all for coming in today, and we hope you have a wonderful weekend.